Welcome to our lecture on the DC microgrid and the control system. We shall today discuss in detail that modeling of the DC microgrid, that is the microgrid dynamics and its modeling. So let us consider that first the power conditioning system. So, what you have? You have a one PV and thus you got a PV link that will transmit the power, and ultimately you will track the maximum power point and all those things. For this reason you got a DC to DC converter. One DC to DC converter will try to track the MPPT, another DC to DC converter will give you the desired voltage level, and thus you come to the DC link, and from this DC link this is the entry point, and there it may require to have a pre-processing to get the desired DC bus voltage, and thus you have this grid connected inverter, and you have a grid link. Essentially it is a PWM inverter, and for this reason it will inject high frequency harmonics, and to bring down that harmonics level to the desirable level you have the filter, essentially that is your grid link. So, for this reason we can say that let us consider this two stage conversion of the PV interconnections with the grid as shown in the figure. So, first part is your DC part, and if it is a DC microgrid, so yeah, and this is essentially you have to be this is essentially the follow with the active power filter and all those things, or active rectifier. So, this part is essentially a DC to AC conversion, and thus what you can say that this is a block diagram of the grid connected PV system with two stage power conversion. This is one stage and another stage where PVSC. So, this one it is the PV side converter is the PV side converter, and GSC essentially it is DC to AC is a grid side converter. So, both the converter you require to place it. The PV link is interfaced between the PV source circuit and the SB and the PVSC, that is PV side converter, and that require a link essentially, and the task of this link to mainly if it is a pure DC it does not matter, but since it has a switching. So, we require to if it is a buck converter. So, what happen, you are temporarily making a connection off and you are maybe bucking. So, then what will happen, the MPPT point will be shifting maybe, and thus you require to sink some amount of the current in this capacitor and you have a ripple. So, this PV link will be this combination of the capacitor inductor, and that gives you a ripple free voltage at the input to the PVSC. So, for this reason what we can say, it provides filtering function to maintain steady voltage at the link. And what happen, and sometime you are shorting if you use a boost converter. So, that also you require to consider. So, for this reason we require to have that filter, so that current value does not fluctuate a very high extent. The PVSC is a DC to DC power interface, the input of which is coupled to the PV link and is usually controlled by the maximum power point tracking algorithm, so that the maximum energy harvesting is achieved, so that we can take what solar generate at max. Thereafter, let us come to the power conditioning unit. So, your MPPT voltage depending on the string length and all those things, you are generating some kind of DC voltage level, but your DC bus has been connected to the maybe the 48 volt, and for this reason you require another DC to DC converter to this, and that will be mentioned as your grid PVSC. And similarly, if you are injecting power to the grid, then you require AC to AC conversion, and that will be named as grid side converter. For this reason, what we are saying that grid link in the interface between the DC grid and the grid side converter, it provides the filtering function to guarantee the power quality as required by the grid code. So, whatever the grid code, it will be specified by the particular state of the law. So, you have to follow that. The transformer can be implemented at this stage for the purpose of the galvanic isolations and the voltage conversion, because after that it is a DC to AC stage after inverter, and if you wish to connect a high volt, you generally hook up to the high voltage, and for this that depends on which point you do the power, which point means which voltage level you evacuate the power, because if you are injecting a huge amount of the power, ultimately you cannot evacuate in a distribution network. You may have to evacuate in a generation or in a transmission network. So, you may if you have a putting a power plant and you are then maybe your generation may be the 5 megawatt. So, you cannot add that power in a distribution level, you have to add that power into this transmission level, maybe the 33 kV bus. So, for this reason you require a step up the transformer, and thus the transformer provides galvanic isolations, and that is also the part of the grid code. Like for the example, that European Union mandatory requirement is the transformer, and but there are some countries like China all does not require the galvanic isolation in a distribution level. The GCS is the power interface between the DC bus and the AC grid link. It converts DC to AC for the grid interconnections. That is the whole purpose of it. The DC bus is commonly formed by capacitors which maintains a steady DC bus voltage between the two conversion stages. Now, this is the figure 2, which shows the DC link grid connected PV power system for the 2-stage conversion. The DC bus is important to interface the PV side converter and the grid side converter in a 2-stage conversion system. First you got a solar panel, there you got a capacitor. I told you, there can be a momentarily blocking of voltage or current, and depending on the topologies of this converter, DC to DC converter, for this you require a input capacitor. And thereafter same way there might be a instantaneous mismatch between this to power generation and then power supply, that has to be fed from or supplied into the storage element like capacitor. And apart from that, till this point it is DC, thereafter it will be the inverter current, and for this reason we require to model this capacitor rightly, so that it can sink that amount of current. So, what we can say here, that the voltage variation of the DC bus is caused by the interaction between the injected current and the extracted current corresponding to the capacitance of the DC bus. So, the current here it is entering and current here it is leaving. If more current is entering and less current is leaving depending on the load, but it is not a problem, because since you can consider grid is an infinite load. So, then voltage may sink, and vice versa, if you are trying to supply the more load, then the capacitor voltage will sink, and thus you have to have a balance existed, because if you are putting charge into the capacitor, voltage will swell, and if you are taking out charge from the capacitor, voltage will sink. Thus, you are required to have a balance between the IDC and the INB. So, what we can write, so dynamics can be represented by C dV/dt equal to IDC is the current that is been generated by the DC to DC converter in the PV side, and ultimately you have fed to S grid side inverter, that value is the INV. So, that ripple current should be equal to dV/dt. More is the difference, more will be the ripple current into the capacitor. Ultimately, C dV/dt will compensate that amount of different amount of the deficits, where DC expressed by the differential equation within the coefficient, and CDC are the two variables IDC and INB, and thus from there we can integrate upon the BDC will be 1 by CDC integration of DC and INV dt, and we want that value of the VDC almost maintain constant. So, the ripple in that capacitor is less. So, there is always trade off in defining the ripple at the PV link. Lower the value of the ripple at the PV link can enhance the MPPT accuracy and the steady state operation. However, you require to put definitely you require to put a higher value of the capacitor. However, it results in a high capacitance appearing at the PV link, which slows down the dynamics. That means, if you want to track or you change the irradiation condition, you require to change one state to another state. So, change will be slower if the value of the capacitor is high. So, value of the ripple voltage should be specified by the loss that caused by the deviations from the MPP. So, that has to be mentioned in your operation, and moreover, due to the nonlinear behavior of the what you are essentially doing is a switching, thus it is on off control, and for this reason it has got a nonlinear dynamics behavior of on off switching. Averaging is required to derive the model for the power interfaces. That is something we require to keep in mind. Capacitors are required across the PV link. Inductor are also needed to construct the PV side of the converter. We require capacitor, so that what happen, you either stop the voltage, that depend on the kind of topology you are using. If you are using a buck converter, essentially for the interval when switch is off, you are stopping the current, and also in case of the boost topology, you are making the source short through an inductor. So, either of the cases, to hold that value of the voltage and a current, we require to put a small capacitor. For this reason, we say that capacitor is required across the PV link. Inductor also needed to construct that PV side converter. Why you require a inductor in the PV side converter? Because it smoothen the current profile, and you got almost steady state value of the current, and it control also become easier. We shall see how the control has been done, and you will find that value of the inductor is essentially try to make the current continuous, and thus you can operate this converter into the continuous conduction mode, and once you are operating in a continuous conduction mode, you have a better control over on your topology. The system dynamics can be expressed in general form, showing the dynamics of the inductor current IL and the PV link voltage, that is VPB, which controlled by the switching duty cycle D. So, DIDT is a function of IL PV and the duty cycle. And similarly, the VPV will be again the function of this same parameter IL, PV and the duty cycle. And thus, we have to take the piecewise linear model, and thus we will give a normalized value thereafter a perturbation. So, what we can find? So, del IL equal to the partial derivation of these functions with respect to dou dv, and thus you can have, that is this delta terms is the perturbation, perturbed, that is small disturbance. So, if you have a, and that is that inductor current will change for the perturbation of the PV voltage as well as the perturbation of the PV current as well as the perturbation of the duty cycle. Similarly, the PV voltage will change for the perturbation of the PV voltage as well as the current through due to the inductor as well as the duty cycle. So, where we say that this delta IL, VPV and D represents the perturbed quantity or the represents the small signals of the PV modules voltage and voltage PV and the inductor current IL and the switching duty cycle D respectively, and SS essentially it is it denotes the steady state value. That means you are not accounting any transient, because once you refer to the transfer function always refer to the steady state value. SS denotes the steady state. The small signal model characteristics, the system dynamics, and is important for the model based controller design. Now, let us take that topology to be the boost, PVSC to be the boost topology. Now, what will happen? The boost converter modeling of the DC link power interface, and based on the schematics of the figure 3, the system dynamics can be derived as follows. When the PV link voltage is the control variable, the output voltage V0 is assumed to be constant for dynamic modeling. So, it is the PV. So, you got IPV, essentially you got a capacitor, thereafter you got an inductor. So, what happen if you do not give the capacitor, ultimately what happen if you short it, then there will be a huge drift in a MPPT point. So, voltage will supposed to collapse at this point, and what will happen, high current will flow and thus MPPT point will change, and this capacitor will ensure that this MPPT point almost stays close when switch on off takes place. So, based on the schematic in the figure 3, the system dynamic can be derived. When the PV link voltage is the control variable, the output voltage V0 is assumed to be the constant for dynamic modeling, and Q on state dynamics, that is L dQL dt equal to PV, C IN PV dt equal to PV minus IL. So, Q off state dynamics equal to L DIL dt equal to PV minus V0. From there you can get C IN dV dt minus PV minus IL. So, here is the equation. So, you have a couple of equations corresponding the on state of this converter, and this is the couple of equations 8a and b are the off state of the converter. So, we should choose the average model here. We have a different kind of modeling. So, we will analyze here by the choosing the average model. The boost converter modeling in the PV link power interface is dL dt equal to essentially 1 by L PV minus 1 minus D into V0, and this what you have referred, please go back, we have referred here this is the function, and here this del f is this. So, this will be abbreviated, was abbreviated there. So, that L d I dt equal to is a function of I L, P V and D, and thus it is linked 1 by L P V minus 1 minus D into B 0. Similarly, this ripple of the voltage in the input side of the converter, that is B d V d t, is C I N I P V minus I L. So, where D is the switching frequency of the control variable, and thus you can write the state space equations. So, converters modeling of the PV link. So, small signal model represents the system dynamics in state space descriptions in the equation 11, and you can convert it to the transfer functions. So, it is a matrix and this is a B matrix, you know how to convert state space to the transfer function. So, this is a state space, that is L d I d t equal, and these are the essentially x dot. This is your A x plus B u. So, this is the A matrix essentially, and this is the U matrix, where U here is the change in the duty cycle. So, the transfer functions, what you can find here is that the B delta P V, that is a voltage change with a change of the duty cycle. If you are large scale, you can remove also the delta. So, essentially you are left with V 0 by L C in, that is a capacitor, input capacitor, and just second order system. That is what we are familiar. If it is a second order system, we can analyze it quite good. So, S square minus 1 by R P P into C n into S plus natural frequency of oscillations comes out from the L and the capacitor input. So, from this what we can say is that where the P V and the I L represents the terminal voltage and the inductor current respectively, these are considered to be constant in this state. The signals I L and V P B are the state variable, and D represents the control variable in the small signal model. Now, let us take a next case, that is the dynamics of the DC bus for the AC grid connection. That means, you are connecting to the main grid and you are converting the power DC to AC. And thus, what happened? This dynamics of this DC bus is described, please refer to the equation 1, where the dynamics of BDC is caused by interaction between IDC, that is the current, it is generated from the this PV SC, and the inverter, the current sink into this grid side converter, and the DC bus capacitor CDC. In case of the single phase grid connections, a high capacitance is applied to the DC bus. So, that what happen? You have a less disturbance. The dynamics of the DC bus voltage can be represented by the interactions of the input power PDC and the output power, essentially what we, since it is an AC. So, you are mentioning at PINV of the DC bus. So, we can rewrite in terms of C dV dt. So, with the suffix DC, that is PDC minus INB by the voltage DC. So, we can equate in terms of power. So, essentially C dVdt equal to I. So, I can be written as a difference of the power by the voltage, and thus what happened in the energy equilibrium. So, C dVdt I equal to 2 PDC minus P grid by VDC, where this one you can rewrite as this is 1 by C DC into 2 PDC minus this can be splitted into the V and I grid side voltages and current by the DC bus voltage, that is 2 Vc, and that we name it as a function H VDC and IMG max, where the DC and the AC conversion losses, we assume that the system is lossless here. So, the variable this V magnitude MAG and the IMAG represents the amplitude of the grid voltage and current respectively. Now, what we can say, so again we can go for the same treatment for small signal operation. So, here the small signal model can be derived for the steady state condition in terms of the constant value of the DC power PDC and the grid amplitude VMG. The small signal model is represented by variation of the VDC bus voltage, that is V delta, in response to the small signal variations of the grid current IMG, and thus we can apply the following linearization process, and thus VDC by dt equal to this H, please refer to the previous slide what is H by VDC is the steady state value DC plus H I G magnitude SS IMG. The small signal model can be derived and can express as dVdc dt equal to minus PDC minus VMG into IMG by 2 DC V square DC minus this term and V magnitude 2 DC into VDC IMG. The small signal model representing the variation in the DC link voltage in response to the multiple change in the grid injections current is expressed by VDC dt equal to minus VMG to CDC IMG. So, this will be your the voltage ripple into the capacitor of this input to the grid side inverter, and thus what we can say, the model shows that the integral characteristics of the DC bus voltage in response to the any small variation in extracting the current from its steady state, and thus what happened, the steady state gain is negative value and is given by the minus VMG by 2 CDC VDC. This allows that any shift from the equilibrium can lead to the DC bus voltage to deviate at a rate that corresponds to the static gain of the small signal model. So, that is something we require to keep in mind. So, this is the some takeaway of this modeling, that this shows any shift from the equilibrium point can lead to the DC bus voltage to deviate at a rate that corresponding to the static gain of the small signal model. So, you can be sure that at which rate this change is occurring. Thank you for your attention. We shall continue in a modeling of other converter in our next class.